Welcome to today's deep dive. We know you're here because you're a learner. You want that thorough, in depth knowledge, but without the massive info overload that usually comes with it.
Yeah, we try to do the heavy lifting so you don't have to.
Exactly. And today's mission is it's unpacking this really fascinating presentation on something called rectangle overlap detection.
Right, which we're pulling from two specific slide decks today.
Hmm.
One is called Efficient Rectangle Overlap Detection, and the other is just linesweep.pdf.
And on the surface, figuring out if two boxes touch, I mean, it sounds like child's play, right?
It really does.
Like if you draw two boxes on a piece of paper, you don't need to do any math to know if they touch. Your brain just, processes that visual information instantly. You glance at it and.
Right, but and this is the catch. If you're a computer trying to design a microchip, it's a different story.
Oh, yeah. A microchip with 3 billion overlapping microscopic wires?
Yeah, exactly. At that scale, that simple visual check becomes a massive computational wall.
Which is crazy to think about. If you use the wrong method, a system could take literally years to answer a question that a kindergartner could solve in a second.
And that scale is what turns a trivial geometry problem into one of the most important bottlenecks in modern software engineering.
So it's not just a theoretical math puzzle.
No, not at all. This specific geometric algorithm is the invisible engine powering our modern world. It sits underneath VLSI design, which is that microchip routing we just mentioned.
Right.
But it also powers collision detection in video games. Like when a character walks into a wall and stops, that's this algorithm.
Oh, wow. I didn't even think about physics engines.
Yeah. And spatial indexing for GIS maps, automated warehouse logistics, even document layout analysis. It's everywhere.
So we're going to trace the journey of this problem today, framing this whole deep dive as a journey of scaling an idea.
Because we aren't just learning some abstract math here.
Hmm.
You're looking at how an algorithm is taken from a basic concept to a highly optimized C plus 20 implementation.
Okay, let's unpack this. Before we can appreciate the clever solution, we have to understand why the obvious solution just fails completely when dealing with large data sets.
Right. What the sources call the naive approach.
Yeah. And to understand that trap, we have to define the core overlap condition first.
Which is pretty strict. For two rectangles to intersect, they have to overlap in both their x dimension and their y dimensions simultaneously.
Right, because if you only check the horizontal x-axis, the rectangles might be positioned directly above and below each other.
With miles of empty space between them.
Exactly. So the mathematical formula checks if the first rectangle's lower boundary is less than the second's upper boundary, while also checking if its upper boundary is greater than the second's lower boundary.
And then it just runs that exact same logic for the axis.
Okay, so that's the rule. But the naive approach takes that formula and just applies it to everything, right?
Yeah. Literally everything.
Yeah.
If you have a data set of rectangles, it takes the very first one and runs that mathematical comparison against every single other rectangle in the system.
And then it moves to the second rectangle and checks it against all the remaining ones.
Which, is perfectly fine for 3 or 4 boxes on a screen. But when you apply this to, say, a geographic information system mapping out millions of building footprints,
The math just collapses.
it completely collapses.
It's like, okay, think about it like a giant networking event.
Ooh, I like this analogy.
If you're in a small room with 10 people, shaking everyone's hand to see who they are is easy. You just walk around.
Takes 2 minutes.
Right. But if you were in a massive convention center with 10,000 people, shaking every single person's hand means 100 million individual handshakes.
The event just becomes entirely dysfunctional at that point.
Yeah, you're spending days walking across the convention hall just to shake hands with someone you have absolutely no business talking to.
And that convention analogy perfectly illustrates what computer scientists call big O of n squared time complexity.
O of n squared, the exponential trap.
Exactly. As the number of items the n grows, the amount of work the computer has to do grows exponentially.
So you're forcing the processor to perform redundant checks on shapes that are essentially on opposite sides of the universe.
Right. Checking a bounding box in New York against a bounding box in Los Angeles is just a complete waste of computational cycles. And in production data sets, structural efficiency isn't just nice to have.
It's required.
It's absolutely required. The naive approach is fundamentally too slow for modern applications.
So the goal is to stop walking across the convention room. We need a system that eliminates all those impossible pairs early on.
So we only check rectangles that are actually close to each other.
Which brings us to the hero of the presentation, the line sweep algorithm.
Yes, the line sweep pattern. This shifts the strategy completely and drops the time complexity from that n squared disaster down to O of n log n plus k, where k is the actual number of overlaps.
Okay, let's walk through the four-step pipeline the sources outline for this. First, it breaks the rectangles down into events, right?
Yeah. Every rectangle creates two specific markers along the horizontal x-axis. It drops an enter marker on its left edge, which gets flagged with a +1.
And then it drops an exit marker on its right edge, flagged with a -1.
Exactly. You're basically stripping away the top and bottom of the box for a moment.
Just looking at where it starts and ends horizontally.
Right. And step 2 is the sorting phase. The system takes all these +1 and -1 events and organizes them by their x coordinate.
From left to right.
Yes. And that sorting is an investment. It takes a little computation up front, but it creates a literal roadmap.
Which leads to step 3, the sweep.
Right. The algorithm moves a vertical reference line from left to right across the data.
Here's where it gets really interesting for me. Imagine a literal laser scanner, right? Like a glowing vertical bar moving left to right over a desk covered in scattered papers.
That's a great visualization.
So the scanner starts at the left edge. As it moves, it hits the left edge of paper A. That's our +1 enter event.
And step 4 kicks in the check phase.
All right. The system takes paper A and drops it into a temporary holding area called the active set. Then the scanner keeps moving right. A few inches later, it hits the left edge of paper B.
So now paper B also drops into the active set.
And because paper A and paper B are now simultaneously sitting in the active set, the algorithm knows they share the same horizontal space.
They're physically near each other.
Mm.
Only now, and this is key, only now does the computer pause and run that y-axis mathematical check to see if they actually overlap vertically.
But wait, let me push back on this for a second. If the scanner is constantly moving left to right, scooping up every paper it touches, doesn't that holding area eventually just fill up with every paper on the desk? Because then we're just back to comparing everything against everything, right? How does the computer know when to stop caring about a paper that the scanner has already passed?
That is the genius of the -1 exit event. It operates as an automatic memory release.
Oh, okay.
The slides actually show the specific command in the Python code for this. It's a pop function active.pop, specifically that removes the item.
So let's trace the scanner again. It just checked paper A and paper B.
Right, and the scanner keeps moving to the right. Eventually, it reaches the right edge of paper A.
Which triggers the -1 event.
Exactly. And the algorithm immediately pops paper A out of the active set. It completely purges it from active memory.
So when the scanner keeps going and eventually hits paper C way over on the right side of the desk, paper A is just gone.
Gone. The computer doesn't even have a record of it in the active group anymore, so it never wastes a microsecond checking if A and C overlap.
Wow. So it's this dynamic, constantly updating list of only the things that are directly under the laser at that exact millisecond.
Yes, it solves your convention center problem because you're only ever talking to the people standing directly shoulder to shoulder with you.
That is incredibly elegant, but having a brilliant algorithm on a whiteboard is one thing. Actually writing it for a machine is another.
And that brings us to the architectural Rosetta Stone slide from the presentation.
Yes. The sources provide this fascinating side-by-side comparison of the exact same logic written in two very different programming languages, Python and C ++20.
And the visual difference is striking. Python uses standard lists and tuples. The code says something like tuple rect rect or none.
It reads almost like plain English. Very clean.
Right. But the C++ version, it uses things like std, optional std, pair, rect rect, and std vector. It's highly engineered.
It looks intense, but so what does this all mean? The presentation explicitly notes that both implementations map to the exact same big O complexity. They're both O of n log n.
Yep, the math is identical.
So if the math scales identically, why did the developers bother going through the pain of writing that strict verbose C++ version at all? Why not just use the readable Python?
Well, because while the math scales identically, the hardware does not.
Oh, interesting.
To a theoretical mathematician, a step is just a concept. But to a computer processor, a step requires fetching physical electricity from a physical memory module.
Okay, I'm following.
Python is designed for human readability, so it's very relaxed about memory. When you create a list of rectangles in Python, the system might just scatter the data for those rectangles randomly across the computer's RAM.
So I'm imagining reading a book, but instead of the pages being bound in order, you read page 1, and at the bottom it tells you page 2 is somewhere on the 3rd floor of the library.
Yeah, exactly.
So you have to walk up there, find it, read it, and then it tells you page 3 is down in the basement.
And that perfectly describes a CPU cache miss.
Cache miss.
Right. Modern processors have a tiny lightning-fast memory bank built directly onto the chip called the cache. It wants to pull data from there because it's instantaneous.
But if the data is scattered randomly in the main RAM, like the library pages,
The processor literally has to halt the algorithm, reach out to the slow main memory, find the data, and drag it all the way back.
and those micro delays must add up catastrophically when you're processing millions of shapes.
They absolutely do, which is why C++20 uses what the slides call zero-cost abstractions. Specifically, it uses std vector to ensure cache-friendly contiguous memory access.
Meaning the data is physically bound in order.
Yes, the compiler forces the computer to allocate a single unbroken block of physical memory. As the algorithm sweeps left to right, the CPU cache just inhales the data sequentially.
The processor never has to stop and search the library.
Never. The math steps are the same as Python, but the physical execution is vastly faster.
That makes so much sense. The C++ version also uses something called compile time evaluation with constexpr, right?
Yeah, doing as much math as possible before the program even runs.
And it has a tool for mathematically safe null handling.
STD optional. This is huge. In relaxed language, if the algorithm checks two boxes and finds no overlap, it might just return a null value, basically handing the system an empty box.
And if the broader software tries to open an empty box,
The entire application crashes.
which, if you are doing VLSI design for a multi-billion-dollar microchip, a random software crash is not just an annoyance.
It's an unacceptable risk. The C++ std optional physically prevents the code from compiling if you forget to write a safety net for that empty box scenario.
Wow. So it forces you to handle the error before it can ever happen.
It provides safety guarantees that a dynamic language just can't offer in high-stakes environments.
Okay, so algorithms and code idioms sound great in theory, but how do they actually hold up when deployed?
Well, the sources give us the hard data on that.
And the performance chart is dramatic. They ran a test with a data set of exactly 1,000 rectangles.
A pretty small data set, honestly.
Right. And the naive O of n squared approach required exactly 1,000 operations.
Because 1,000 times 1,000 is a million,
But the line sweep approach dropped that to just 10,000 operations.
which is an exact 100x speedup.
1,000 down to 10,000. I mean, the sheer scale of the efficiency gains is awe-inspiring.
And that's just at 1,000 rectangles. Imagine a million.
It's the difference between a program running in seconds versus running for weeks.
Exactly. But, an algorithm that runs incredibly fast is useless if it occasionally gives you the wrong answer.
Which brings us to the robust testing detailed in the slides. And I noticed a massive disparity here. The Python implementation passes 14 tests.
Right.
But the C++ version is aggressively tested with 154 test cases, and it has 805 specific assertions. Why the huge difference? Why 805 assertions for C++ compared to 14 for Python?
Well, it loops back to that strict environment we were talking about.
Yeah.
C++ gives you the absolute power to dictate memory for maximum speed, but it strips away the safety nets that Python provides automatically.
Oh, so you can easily write code that accidentally reads memory it shouldn't.
Or deletes an active event too early, yeah.
Yeah.
You're building the engine from scratch, so you have to test every single bolt.
That makes sense. They tested all these edge cases, edge touches, partial Y overlap, no X overlap, empty lists.
Even invalid rectangles. They threw everything at it.
But my favorite part of the verification process was the SVG visual output.
Oh, yes. The graphical tests.
The code literally generates an actual graphic mapping out 11 test rectangles, and it color codes them. Red indicates an overlap, and blue indicates non-overlapping.
It's such a brilliant way to validate the logic.
Right, because human visual confirmation works hand in hand with the mathematical assertions. You can just look at the picture and guarantee the algorithm is behaving flawlessly.
It brings all that abstract and visible architecture right back to physical reality.
It really does. So
Yeah.
bringing this all back to you listening, the next time you use a GPS or marvel at the physics in a video game, you are witnessing the O of n log n magic of the line sweep algorithm.
Sorting those events and checking active sets in microseconds.
It's incredible. But before we wrap up our learning journey for today, I want to leave you with a final provocative thought.
Something directly from the Future Work and Architectural Extension slide.
Yes. The presentation notes that the next steps involve migrating this exact logic into 3D.
Detecting overlapping 3D bounding boxes.
Right. And replacing the active list with an interval tree for even faster checking.
Yeah.
But just think about the geometry of that for a second.
It completely changes the game.
It does. If a 2D environment requires a one-dimensional vertical line sweeping from left to right, what happens when you add a z-axis for depth?
Do you need a sweeping 2D plane instead of a 1D line?
Exactly, like an MRI machine scanning through a room. How does the active set handle shapes floating above or below each other as that plane passes through them?
It's a whole new level of complexity.
It's a fantastic little thought experiment to mull over as you go about your day.
Uh,
Thanks for taking this deep dive with us.